First of all, I want to congratulate Claire on coming here and her medal, and also as the last speaker of the conference, I think we should all thank her for organizing the conference. So that's congratulations, thanks, Claire. Good. So I'm going to talk about measures of irrationality for hypersurfaces of large degree. I think some of you have had the misfortune to hear about this already, but if nothing else, the authorship has changed a little bit. So this started off as a project with two different groups, and we ended up kind of combining forces. So this is now joint work with Bastianelli. It's a big bunch of people. Bastianelli, Dufoy, I'm. Is this enough people? I'm and Dufoy. Let's start by considering a smooth hypersurface in complex projective space. Let's say degree d. So I'll always use the notation xd in Pn plus 1, and I'll always work over c. So I'll use my varieties, and so on will always be n-dimensional. So this is a hypersurface of degree d. And as you know, it's a very interesting and subtle problem when d is small to try to determine whether or not such a hypersurface is rational. There's been a lot of progress on this kind of thing, due in large part to Claire, also Janos and others. But if the degree is large, then it's very elementary, of course, that x is irrational. So if the degree is at least n plus 2, then such a hypersurface is irrational because it carries non-zero homomorphic forms. So the question I want to talk about today is how irrational is it when x is large? So in a vague sense, the question I want to address today is that, in quotes, how irrational is such an x when d is very large? So if you take very large degree hypersurfaces, in some vague sense, I want to ask how irrational do they become? Okay. So the first thing we should sort of ask about is what do you mean by this? How can you measure irrationality? So let me start by talking about, in general, various measures of irrationality. Okay. So what's the one case when it's really pretty clear how to measure how irrational a variety is? Well, that's in the case of curves. So in the case of curves, the natural measure of irrationality is the gonality of a curve. So let me recall that if you have an irreducible curve C, then a projective curve, then the gonality of C is the least degree of a branch covering, the least degree with which you can express the smooth model of C as a branch covering of P1. So the gonality of C is the minimum of all the degrees of branch coverings, let me say C prime to P1, where C prime is the normalization of C. So all these invariants are supposed to be birational invariants. So we look at the gonality of the smooth model of C, and so of course then the gonality is 1, if and only if C is rational. So one thinks of the gonality as measuring how far a curve is from being rational. And then the answer to this question would be an elementary old theorem of Noether, which says that if you take a smooth plane curve of degree d, its gonality is a smooth curve, then its gonality is d minus 1. And there have been a lot of results bounding the gonality of various sorts of curves. Okay, so now the question is, what's the natural way to generalize this definition to varieties of higher dimension? So now let's consider an irreducible projective variety of dimension n. And then the question is, what invariance can we define that kind of extend the ganality. And there are a number of things you can do. So I'm going to mainly focus on 3 of them, and then there's some others I'll mention in a minute. So let's start with, so here's the definition. I'll put it on the next board. So the first invariant I want to look at are what people call the degree of irrationality of x. So this is the most direct generalization of the ganality of the curve. So we take the minimum of the degrees of all rational coverings. Wait, something is that. Am I not on? Something's happening here. Okay.
You have some now.
Now I'm on. Okay. So it's the minimum of all the degrees delta so that there exists a rational covering x to Pn of degree delta. So it's the least degree with which you can express x rationally as a covering of Pn. So that's the degree of irrationality. I'm going to put a second one here. The third one I'm going to look at is what you might call the covering ganality of x. So this is going to be an invariant that's defined by reducing things back to curves. So we ask, what's the least ganality with which we can cover, for which we can cover x by a family of curves of that ganality? So this would be the minimum of all integers c bigger than 0, such that given a general point on the variety, general point x on a variety, there exists an irreducible curve of ganality c passing through x. So with the ganality of this curve less than or equal to c. So we look at the minimum ganality of a family of curves covering x. And then in between these, you can define, you could look at what you might call the covering ganality, but I'm not going to say much about it. So this is the minimum of all c, so that 2 general points of x can be joined by a curve of ganality less than or equal to c. So general points x, y, and x are connected by an irreducible curve c of ganality less than or equal to c. So these are 3 different integers, and in the one-dimensional case, they all reduce to the ganality, but in higher dimensions, they're different. And the way to think about these is that these measure the deviation from various natural rationality properties that a higher dimensional variety can have. So clearly, by definition, the degree of irrationality of x is 1 if and only if x is rational. So when is this covering ganality 1? When can you join 2 points by a curve of ganality 1? Well, remember, ganality 1 means rational, so covering connecting ganality 1 means that x is rationally connected. And what about covering ganality? Well, that means that you can cover x by rational curves, so that means that x is unirolled. Okay, so these are the kind of the 3 basic measures, and in general, there's an inequality among these, namely, okay, so there's the inequality in general. The covering ganality is, well, it's obvious that the covering ganality is less than or equal to this connecting ganality, and this is less than or equal to this degree of irrationality. So this inequality is obvious, and this inequality comes about because if you have something that's a covering of Pn and you look at the inverse degree delta covering of Pn, and you look at the inverse image of lines, that gives you a family of curves of ganality delta covering x. And there are other invariants you can look at. So Claire showed us one. I'm not going to define it very carefully, but it's a Chow theoretic invariant let's call it v of x, that's less than or equal to the covering gonality. And you look at the least degree v so that you can cover x by one parameter families of Chow constant cycles of that degree. Okay, and so for today, I'm mainly going to be talking about this degree of irrationality and the covering gonality. So let me say a word about the history. So I think actually the first reference I know of where people looked at this degree of irrationality were some people in the commutative algebra community, so Heinzer and Moe. And then there are a series of papers by somebody called Yoshihara who computed these things for some classes of surfaces. This covering gonality, again, people had looked at it in passing, but I think the first time I'm aware of when people looked at it kind of seriously as a measure of rationality was a paper, maybe it's the thesis of Bastianelli under the direction of Puella, who computed it, for example, for the symmetric square of curves. So, but I'm going to try to convince you that these are kind of interesting invariants, and there are some interesting questions that come out of them. Okay, so let's do some examples. So one of the fun things here is we can actually look at some fun examples. Okay, so let's start with examples of covering gonality. Okay, so let's look at some examples of covering gonality. Okay, so covering gonality. Okay, so the first thing, what about a surface, a hypersurface, a surface of degree d in P3? So let's consider a surface, a smooth surface in P3 of degree d. And then I claim that the covering gonality of such a gadget is at most d minus 2. And so why is that? So I need to cover x by a family of curves of degree d minus 2. I do this by, so if I take so let me take a point on my surface, and then I look at the tangent plane to the surface at that point, and I intersect it with the surface, and then I get a plane curve of degree d with a singular point. And if I have a plane curve of degree d with a singular point, that has gonality less than or equal to d minus 2. So the point here is that the gonality of the surface intersect the tangent space is less than or equal to d minus 2. So in that way, I cover my surface with curves of gonality d minus 2 or less. If I were to go up in dimension, I can do a little bit better. So if I look at threefolds, surfaces of degree 3, dimension 3 or higher, so if I take xd in Pn where n is at least 4, well, I can do a little bit better, because if you do the dimension count, you'll see that, well, you really have to do it only for threefold. The threefold is going to be covered by plane curves with triple points. So here the covering gonality is less than or equal to d minus 3. And again, as the dimension goes up, you expect to do a little bit better. Let's take some, so for example, let's take x to be a K3 or a abelian surface. And I claim that for these guys, the covering gonality, well, it's less than or equal to 2, and though therefore it's equal to 2. So why is that? Well, if you take, let's say, a K3 surface, it's well known that it's covered by a family of singular elliptic curves. So those have gonality 2. And similarly, if you have an abelian surface, it's covered by curves of geometric genus 2 or less. So again, that has gonality, those have gonality 2. You can also ask about covering gonality of spaces that are important in their own right. So for example, what about the moduli space of curves? So of course, I don't really have anything serious to say about this, but you can contemplate the question. So what can we say about the covering gonality of the moduli space of curves of genus G? So what does it mean to compute this? So you're asking yourself, if you take a general curve of genus G, you'd like to write it, put it as a fiber in a one-parameter family of curves so that the parameter curve has relatively modest gonality. So I don't know a good answer to this, but there's some kind of silly answer. You can give, you can bound it by a Hurwitz number. So the interesting question is to find a realistic thing. But in any event, this is certainly less than the Hurwitz number of simple coverings of P1. Let's say S to P1 of degree G plus 1 with genus of S equals G with fixed branch points. So this is some big number, but anyway, so this is some bound. But it's a fun question. I don't know what you might expect. How do you find what kind of one-parameter families can you put a general curve in? No, I think I talked to Sam about that. So there you might get really upper bound, lower bounds. Of course, it's... I can't hear you?
Individual set? No, I asked about AG.
Okay, let's do some examples of degree of irrationality. So examples of the degree of irrationality of X. Okay, so sort of the basic example is just as in the Noether case. If you take a hypersurface of degree D in a Pn plus 1, then you project from a point and you see that the degree of irrationality is less than or equal to D minus 1. So this is kind of the Noether number there. But one of the interesting things that happens that we learned in this paper of Bastianelli and others that I'll mention in a couple of minutes is that unlike the case of curves where the answer is uniform, in higher dimensions, there's some variability. So here's a construction that gives you examples of surfaces where the degree of irrationality is less. So let's consider a surface of degree D in P3, and so a smooth surface of degree D in P3, and suppose that it happens to contain two disjoint lines. So containing disjoint lines L1 and L2. Okay, and so the claim is that if you have a smooth surface containing disjoint lines, you can get a covering of P2 rationally of degree D minus 2 or less. And how do you do this? So let's draw the lines. Okay, so here's L1, here's L2. So let's take a point x1 on L1 and x2 on L2, and let's look at the line joining x1 and x2. So the point is that if I look at this line joining x1 and x2, it's going to meet this surface of degree D in D minus 2 residual points. So let's just say that the line x1, x2 meets the surface x in D minus 2 residual points. Now, if I look at the family of lines joining the point, meeting two given lines, that has the property, that's called a congruence of lines. These are going to come up again. It's a two-parameter family of lines. But it has the property that if I take a general point of, it's what's called a congruence of order 1. If I take a general point of P3, this line will meet, only one of these lines will meet and go through that point, which is to say that if you look at two lines in the plane, you see one apparent double point. So what this means is that then if I take any point on my a general point on my surface, there's only going to be one pair of these, one point x1, only one of these lines that pass through that x, through that point. So this gives me a rational covering from x, well, to L1 cross L2 of degree D minus 2. And of course, L1 cross L2 is birational to P2. So this gives me a covering of, rationally, a covering of P2 of degree D minus 2. So the point to note here is that, of course, if I take in large degree, it's rather special for to find a surface that contains two lines, but on the other hand, I can do it for all degrees D. And then the third example is you might ask, well, what happens if I allow mild singularities? So let's consider xd and Pn plus 1 with an ordinary n-fold point. So just a point of multiplicity n. And the point about multiplicity n is that these still have canonical singularities. So it's singular, but still has canonical singularities. And then if I project from that point, I end up with a covering. So I take a surface, I project from an n-fold point, I get a covering of Pn of degree d minus delta. So this shows me that then, well, the covering ganality of x is less than or equal to the degree of irrationality of x is less than or equal to d minus delta. So if I allow myself to have mild singularities, I can get things down to d minus n. Okay, so those are some examples to keep in mind. Okay, so what are some results for hypersurfaces? So let me now state some results. So results for hypersurfaces. Okay, so the thing that got there's a very nice paper by Bastianelli, Cortini, and Depore a few years ago in JAG, and this is kind of what piqued our interest in these things. So let me start by saying what they did. Okay, so Bastianelli, Cortini, and Depore. So henceforth, this will be BCD. So they wanted to compute. They were thinking of this as a kind of a generalization of Noether's theorem. So they wanted to compute this degree of irrationality for hypersurfaces, and they succeeded for surfaces in threefold. So let me tell you what they did. So we consider again a smooth hypersurface xd and Pn plus 1 of degree d. And they showed two things. So first of all, in all dimensions, they got a lower bound on this degree of irrationality. So they showed that, well, if d is at least n plus 3, then they showed, and I'll explain a little bit later what they did. They showed that the degree to irrationality can't be too small. So it's at least equal to d minus n. And then one wants to try to compute this degree of irrationality. Now again, as we've seen, what we're expecting is some variability from hypersurface to hypersurface. So their idea was to look at what happens for a very general hypersurface, and what they sort of treated the case in 2 and 3 dimensions. So what they showed is if you're talking about a surface or a threefold, and x, so let me say 2 or 3, so 2 or 3, and x is a very general surface or threefold, is a very general surface of degree. So in the case of surfaces, it should be at least 5. In the case of threefolds, it should be at least 7. Then what they showed is that for surfaces or threefolds, this degree of irrationality for a very general hypersurface, very general surface or threefold, is d minus 1. And if you increase the degree by 1, actually, in fact, then the only maps of degree d minus 1 are projection from a point. And they conjectured that the analogous statement is true in all dimensions. Conjectured ditto in all dimensions. Okay, so let me tell you what the results are, and then I'll kind of explain where they come from, and then at the end we'll go back to their very nice argument. Okay, so the first result is a bound on the covering ganality. So that's going to kind of recover this statement. So the assertion is this. So let's assume that we have an arbitrary smooth, well, hypersurface of degree d in p plus 1, and we'll assume it's either smooth or has at worst canonical singularities. Canonical singularities. And then the assertion is that this covering duality is at least equal to d minus m. And so if you allow these canonical singularities, and we've seen this is actually the best you can do. But Bastianelli and Ciliberto and some others actually have computed this for a general thing, and I'll tell you about that at the end. And then the second theorem is this conjecture is the conjecture of BCD. So we now assume that X is very general in P n plus 1 is very general of degree 2n plus 1. And then the irrationality is equal to, the degree of irrationality is equal to d minus 1. And okay, so this was their conjecture. So that then the degree of irrationality is equal to d minus 1. So just as in the case of surfaces in threefolds, and if you go up one more in degree, if d is at least 2n plus 2, then the extremal cases are projection from a point. So then x to Pn of degree d minus 1 is projection from a point. Okay, so that's the result. So it has a slightly, as I said, Ein and Ulrich and I originally did this for. The question is where the things start. So we originally did this for d at least 3n, then Claire showed us how to improve it, and then using that, Bastianelli and Dupuy sort of brought it down to this. So I'm not sure that these are kind of the best possible things, but this is kind of the natural thing given the method, as you'll see. So I'll come back to that in a minute. Okay, so these are the results. So now what's the idea? So, so why is it that if you have a hypersurface of degree at least n plus 2, it's irrational? Well, that's because it carries some holomorphic forms. And so the idea, the natural way of trying to measure irrationality is to study positivity properties of the canonical bundle. But you don't want to just ask how many pluricanonical forms you have. You want to ask how positive they are in the sense of separating points. So now let me say a couple words about a birational, how you can measure birationally the positivity of the canonical bundle. So birational positivity of a canonical bundle. Okay. So let me start with just a general definition. Again, this has appeared under different names before, but the idea is one way of measuring how positive a line bundle is you could ask, I mean, for example, to say the line bundle is very ample means that the sections of that line bundle separate any 2 points. Or you could ask that any 3 points impose independent conditions on the sections of that line bundle. So that's basically what we want to look at, except we want to have a measure that's birationally invariant. So we'll allow ourselves to have a kind of an exceptional set that we don't worry about. So here's the definition. So let's start with X will be an irreducible projective variety. You could imagine it to be smooth. It doesn't really matter, of dimension n. And let's say for the moment, let's just do this for an arbitrary line bundle. Say we have a line bundle on X. So I want to measure birationally how many points such an L can separate. So I'm going to define a condition that we'll call BVA for birationally very ample. So we'll say that L satisfies BVA. So BVA stands for birationally very ample if the following is true. So the condition is we should be able to find a proper closed subset of X, which is going to be kind of an exceptional locus. So that if we take any finite set or finite subscheme of length p plus 1 that's disjoint from Z, such that if C is any finite subscheme or finite set of length p plus 1 that's disjoint from Z, C, the support of C intersects Z is empty, that then C should impose independent conditions on the sections of L. Okay, so the assertion is that then we should have, for any such thing like this, we're asking that the sections of L, if we evaluate them at C, that map should be surjective. So any p plus 1 points should impose independent conditions on the sections of L, except that we allow ourselves to ignore any p plus 1, any subscheme that meets this exceptional set Z, which is what makes this birational variant. Okay, so what is this saying? Let's just see what this says. So what does it say if p is 0? So this says if we take a general point, a single point, the map from H0 of L to H0 of L tensor O of that point should be non-empty. So this just says that H0 of L is non-zero. That's not very interesting. What if we take P to be 1? So then we're saying if we take any pair of points, ignoring this Z for the moment, that those 2 points should impose independent conditions on the sections of L. So that means that the rational map defined by L is birational onto its image. So this means that L defines a map that's birational onto its image, which people sometimes call birationally very ample. Similarly, if P were 2, we'd be asking that any 3 points, that L defines a rational map in which any 3 points map to a span of 2 plane, except that we're allowed to ignore all triples of points meeting this exceptional set Z. Okay. So this is somehow a measure of how positive this line bundle is. And so, of course, the idea will be that that when we apply this to the canonical bundle, this will lead to bounds on these invariants. So let's do some computations, which are kind of, let me just point out some computations. So let's see some examples for the canonical bundle. Well, okay, so if we take, so let's take hypersurface of degree D in Pn plus 1. Okay, so what's the canonical bundle? Well, the canonical bundle is D minus n minus 2 times a hyperplane bundle. Now, if you take multiples of a very ample bundle, then the amplitude is at least this integer here. So this is, this satisfies this condition with P equal to D minus n minus 2. And in fact, the same thing is true if we allow X, if we look at the desingularization of a hypersurface with canonical singularity. So ditto if X prime is the desingularization of a hypersurface with canonical singularities. Right? Because if we have something with canonical singularities, the pluricanonical forms upstairs pull back from downstairs, and again, everything's birationally invariant. So, but here, of course, the exceptional locus of the desingularization would be the set Z we need to imply, to look at. Okay, so this tells us something about the positivity of hypersurfaces. And then what about the example of plane curves? Well, here you'll see where, as you kind of probably know, this is where gonality comes into the picture. So let's say C is a smooth plane curve, a smooth curve, rather. Then to say that this property BBA P holds for the canonical bundle is to say that, let's see if I can get my holds for the canonical bundle. Let's see if I can get my numbers right. Yeah, so this is equivalent to saying that the gonality of C is at least P plus 2. Right, so for example, if you have a non-hyperelliptic curve, how do you tell if it's trigonal? That's if the trigonal divisors, so that's when this fails with 1, right? Because the trigonal divisors span lines in canonical space. So you read off the gonality of a curve from this positivity of its canonical bundle. And this is, of course, this is one of the proofs of Noether's theorem, because by Noether's theorem, you know that a plane curve is this property holds with d minus 3, and so the gonality is at least d minus 1. So that's Noether's theorem. Okay, so what are the, so then how does this, how do these invariants, how do these positivity properties reflect themselves in these measures of irrationality? So now let's, so positivity of kx and measures of irrationality. And these measures of irrationality. So let me first of all prove this, this first statement. So this is a kind of a theorem in quotes. So usually a theorem in quotes means that you're not sure if it's true. This I'm pretty sure is true, but it's so elementary, I'm not sure you really want to call it a theorem, but that's why the quotes are there. But anyway, so the first statement is, let's assume, so we have, let's take X to be a smooth projective variety of dimension n. Okay, and so the first result is that let's assume that the canonical bundle of X satisfies this positivity property BVAP. And then the claim is that the covering gonality of X is at least P plus 2. And hence also the other invariants. So then the covering gonality of X is at least P plus 2. Okay, so this implies the first theorem, right? Because we've said that if you have a hypersurface with canonical singularities, you get this much amplitude. So you add 2 to it, and so the covering gonality is at least d minus n. So this implies that first theorem. And so this is completely elementary, so let's see how this goes. So let's say we have a covering family of curves. So let's say that C sub t is a covering family, is a family of curves that cover X. And these might be, when we talk about these irrationality measures, we're allowing the curves to be singular. So let's let the C prime t be the normalizations, the normalizations. Okay, so we can draw a little picture like this. We have a family of smooth curves. Okay, so let me draw a little picture. So we have, I call it C prime to t. We have a family of smooth curves parameterized by some t, and these kind of cover X, but they may go down singularly like that. Okay, now the point is that the point is simply that if you have a family of curves, family of anything that covers a variety, then if you take the canonical bundle, well, let me just say this like this. Then for general point t in the parameter space, the canonical bundle of CT is at least as positive as the pullback of the canonical bundle from X, just because this is the, let me write like this, restricted to CT prime. So when you pull it back, you get this plus possibly something effective. Okay, so the covering, the positivity of this is at least the positivity of the, and the effect, when you add an effective divisor, that doesn't hurt, that only helps you for these positivity properties. So this says that the canonical bundle of this CT prime satisfies, is at least as positive as the canonical bundle of X, BVA sub P, and so by what we said before, the gonality of CT prime is at least P plus 2. Okay, so that's that. So what's kind of more fun, although less general principally, is the proof of this, is this stuff, the computation of the degree of irrationality for hypersurfaces. So let me explain that next. And really the essential point here is this very nice kind of piece of projective geometry that, that Bastianelli and Cortini and Dupuy do. So let me now talk about the proof of theorem B. So this is that if you take the irrationality, the degree of irrationality of a very general hypersurface is at least d minus 1. And I'm going to do this under, this is the case when it's simplest. So I'll assume that the degree is a little bit larger than it turns out to have to be. Okay, so what's the idea here? So let's consider an irreducible covering. So let's consider f from xd to pn. So xd, again, is xd as always is a smooth hypersurface of degree d in pn. And so let's say that this is a covering of degree delta, irrationally a covering of degree delta. And we already know that delta has to be at least d minus n. And since we're looking at, we want to know what's the minimum, we might as well make it less than or equal to d minus 1. So we're in this range. Okay, so now let's look at a general fiber of this covering. So we'll call that Z. So if we pick for a general point, let's pick a general point y in the target, Pn. Let's let Z sub y be the fiber of F. So this is a finite subset of X, which is in turn living in Pn plus 1. So this is a finite subset consisting of delta points. Okay. Now the very nice observation of BCD, and I'll explain where this comes from a little bit later. The very nice observation, so the very nice piece of projective geometry is that these fibers actually have to lie on a line. So again, assuming, well, we're assuming, so if, let's say if D is at least 2n plus 1, but we're already assuming that, then the point is, what BCD show is that, so let me call this star, these points actually are all collinear in projective space. So the fibers ZY span a line LY in X, well, which is then also in Pn plus 1. So this is their kind of main remark, is that the fibers of this map actually have to be, if you think of the fibers as living in projective space here, they actually have to be collinear. Okay, so in classical language, as I mentioned before, this says that these fibers, these lines form what's called a congruence. So it's an n-parameter family of lines. So form a congruence of order 1, and they show that it's of order 1, which means that again, there's only one of these lines. There's only one of these lines through a general point. Okay. Okay. Now, what they did, how did they prove their result? First, this is Bastianelli, Cortini, and Dupuy. I mentioned them a little bit earlier, right? This is this paper. So what they did is, so people have looked very hard at these congruences in low dimensions, and it turns out that what they noticed is that if you look at the fundamental locus for such a congruence in dimensions, well, in P3 or P4, So the fundamental locus is where there's a lot of lines through a given point. Then it has to, it always, by they're classified, and it happens that they contain rational curves. And so then they argued that your x, if this had, your x would have to contain a rational curve, and so if d is small, the x contains a rational curve, and so that doesn't happen. So that was somehow their thing. But we want to, I mean, if you slightly vary the argument, it becomes independent of dimension. So let's look and see what's really happening here. So let's write, so let's look at these lines intersect x. Now x has degree d, so this is going to be the point, the fiber, so plus some residual thing, fy, let's call it. So this is a cycle, this is a zero cycle of degree delta, and then of course this has n d points altogether, and so this has degree d minus delta, which we already know is less than or equal to n. So if we look at the sort of intersection of the surface with these lines, we get the fibers of the map plus these fy's, which lie in the fundamental locus of the congruence. Now, the remark is simply this: let's let y vary over a line or a rational curve so these lines are parameterized by Pn minus 1, right? Because they're the fibers. I mean, the lines are coming from the target of this map. So let's let y vary over a rational curve, or a line would actually do the trick. So let's say a rational curve, lambda in Pn. So we have a rational curve of lines. Well, what happens? So the point now is that if we look at these residual things, okay, so we look at these will sweep out some curve, and this curve maps to this rational curve with degree d minus delta left. So these things sweep out a curve of gonality. It might sweep out various curves. They might be gonality at most d minus delta, which is less than or equal to n. And this is where we use the fact that it's not projection from a point, because if it were projection from a point, then the fy's are just this one point. But as long as we're not projecting from a point, these residual gadgets sweep out, yeah. So far, nothing. I mean, x is smooth. I mean, we need d at least 2n plus 1, something like that. No. Well, yeah, so I'm about to say that. So, but z has to be, delta is pretty close. I mean, delta has to be pretty big. So delta has to, we know that delta is already at least d minus n. So, I'm not sure. I mean, is that what you're asking? Oh, I see. I mean, what I'm about to say, that it fails to impose independent. Yeah, no, that would be enough, I think. Right. So I'm about to say that. Yeah. You might want to know that they're kind of, yeah, no, you don't need to know that it's a phi, right. And that's going to come up in a minute. Yeah. Okay. So, and so these fy's sweep out a curve of bounded gonality. And then the point is that there's this famous old work of Claire and Lawrence Ein that says that you can't find, I mean, that if you take a curve on a hypersurface, very general hypersurface of sufficiently large degree, they have lots of forms. So if you, what then show is that if d is at least 3n, and then a very general x, then a very general xd contains no rational, no curves of gonality less than or equal to n. So we get a contradiction if the delta is too small. And then, as Claire points out, what actually has to happen is it turns out, I mean, we're just looking at one parameter family of these, but if you're more careful, you can find a higher dimensional family. If you have a higher dimensional subvariety of low covering ganality, then this inequality gets improved. And so there's some improvement there. So now let me next explain where this, so Claire was alluding to this. Where does this, what's this argument? So this, I think, goes back to, well, in some sense it goes back to Mumford, but I think the idea here is, so this statement star was that these points lie on a line. So this is, I think, an argument Pirola, due in effect to Pirola. So star said that these fibers span lines. So let me show you where this comes from. So this is a nice argument. So the idea is you look at the trace map. So in general, if you have a covering, a rational covering, then by Mumford, there's a trace map that takes canonical forms on the source, in this case x, and you add up along the fibers, average along the fibers, and you get canonical forms on the target, which of course in this case are 0. But what does this really mean? So what this means concretely, this means that, so the zy is a fiber of this thing. So what does this trace map mean? If we take a form here, which is 0, I mean, we take a, well, let me just write down. What this means is that the zy's satisfy Cayley-Backrack property with respect to canonical forms with respect to kx. So in other words, if we take a, i.e. if we take a canonical form on x that vanishes at all but one of the points of the fiber, then it must vanish on the remaining one. Because if it didn't, it wouldn't trace to 0. So any that vanishes at all but one of the points of the fiber must vanish on the remaining one. Vanishing at all but one of the points of zy vanishes at the remaining one. Again, otherwise they couldn't trace to 0. Okay, so these fibers satisfy Cayley-Backrack with respect to the canonical bundle of x. But now the canonical bundle of x is quite positive. So kx is what? Is d minus n minus 2 times h. And this is pretty close to the, I mean, you're pretty close to the maximal number of points. I mean, you're close to the point where it's just automatic that this couldn't happen. So you're close enough to the maximum that you can show that they lie on a line. So there are a number of, let me just, okay, let me tell you one. So an interesting question, which, so there's a very nice kind of further development of this due to Bastianelli, Chiliberto, Flamini et al. So there's I don't think there are a bunch of people, but let me, so Bastianelli, Chiliberto, Flamini, and others. So there's not a manuscript, so let me just at the moment, so I apologize. So you can carry this farther. It's a very nice argument, and you can, so the natural question is then if you take a very general hypersurface, what's its covering ganality? So we said that it's at least d minus 1, but they've effectively computed it in all cases, within 1 or 2. So here's the result. So you fix a very general, for a very general xd and pn plus 1. I'm not sure exactly where it starts. So let me say d not too small. Probably, so at least 2n, but maybe a little bit bigger. Small. So they've essentially computed the covering ganality to within, there's in almost all cases, and to within 1 in the remaining cases. And what turns out, so the covering ganality of x is, so it's basically d, it's approximately, asymptotically, it's d minus twice the square root of n. So it doesn't grow like d minus n, it grows essentially like d minus square root of n. And where this number, essentially where this number is coming from is that if you ask yourself what inequality you get by looking at plane curves, so you look at plane curves with triple points or go up in dimension, plane curves with quadruple points and so on, and you'll get something that grows roughly like square root of n. And so that's somehow where these numbers come from. So let me tell you what the idea is there. So this is really what Claire was hinting at before. So I think the argument is actually quite elaborate, but I can tell you what the idea is. So, okay, so here's your hypersurface. And let's say you have a curve, and you have a G1D, oh, that's the bad notation, a G1C on this curve C. Okay, now, again, if you look at the just as before, as Claire says, and we know that C is relatively small. So just as before, the fibers of this map have to be collinear. So that's as before. Okay. But now think about it. By the same argument we gave before, okay, so the fibers of this map, the fibers of this G1D, they'll be collinear, and they'll cut out the G1D on C plus some other points. But by the same argument we gave before, you better not have, like those other points, better not be two of them, otherwise you'd sweep out a hyperelliptic curve. So actually, by the argument we gave before, what actually has to happen is that all these things have to pass through one point. So the intersection of all these G1Ds have to be these lines have to be the G1D plus one fixed point. So what happens is we're in this situation where you have this family, you're sort of covered by this family of lines that have D variable points and N minus, I'm sorry, this is D, C variable points and D minus C, one point of multiplicity D minus C. So then you can, this is kind of the key geometric thing. So you look at that, and then it's a rather elaborate argument. But anyway, so this is what comes out. And there are a bunch of interesting questions. So maybe I'll just mention one, and then I'll stop. So, so you could first of all ask, for example, what happens for complete intersections? And I think that's already not obvious, because it's not obvious to me. I mean, there's some obvious bound for complete intersections that's linear in the degrees of the defining equations, but I would think you would get something more multiplicative. But let me just ask one question that I kind of enjoy. So let's let SD LD be a polarized K3 surface of genus D. So in other words, LD squared is 2D minus 2. And let's make it general. So take a very general polarized. Okay. So what we've seen is that the covering ganality of these things doesn't have anything to do with the polarization. It's always 2. But the question now is, what can you say about the degree of irrationality? So the question, maybe I'll call it a conjecture, is that the lim sup as d goes to infinity of this degree of irrationality of xd is infinite. So in other words, as you take larger and larger degrees of the K3, you expect it to be, so in other words, you don't expect to be able to express all K3 surfaces as covering with bounded degree, basically. But now, one thing that's amusing here is that I would have expected that somehow you might, so of course the methods we've been talking about don't say anything here because there's no positivity to the canonical bundle. Now I would have expected that actually this degree of irrationality grows linearly indeed. But a nice remark of David Stapleton is that in any event, it grows sublinearly. So that this thing is less than or equal to constant times square root of d. So it's a little bit subtle. I mean, it's not going to grow linearly. So at best, it grows sublinearly. So, but in the end, you could say the same question for abelian surfaces. And there are other questions too, but I'll end there.